Hello everyone, welcome back to the Artificial Intelligence series in Electromind. So in today's video, we are going to learn about adversarial search methods and the Minimax algorithm in very simple and easy to understandable way. First, adversarial search is a search technique used when multiple agents compete against each other. So, in previous topics, we have studied search algorithms like uninformed search and informed search, which include breadth first search, depth first search, uniform cost search, where only one agent tries to find the solution in all those methods. But in many real world problems, especially in game environment, there are two or more players, and each player tries to defeat the other player in a game environment. So, such environments are called as multi agent environments. So, when two players with conflicting goals explore the same search space, this is called as adversarial search. This technique is mainly used in game playing artificial intelligence environments like chess, checkers, and tic tac toe problems. Then, what is the need for adversarial search? So now, why we need adversarial search, especially in the real time, real world environments? So it helps an agents to predict the opponent's move and plan the strategies accordingly. It makes smarter and competitive decisions against the opponent. It makes the game's environments more intelligent and dynamic. Instead of making random moves, the artificial intelligence can think ahead and choose the best possible move. This is what makes modern games are challenging as well as interesting. So if you see the game scenarios, there are different types of game environments are available. So we can classify the game environments into five categories. So first is the perfect information games. So here all the players can see the complete game state. Say example chess, checkers, go game and all. So both opponents, all the game players can able to see the complete game states. Next is the imperfect information game. So here the players may not have complete knowledge of about the game. Say example, if they are playing the card games or poker games, definitely they may not know what kind of card they are having in the hand. Then next is the deterministic game. So here the randomness, right? Randomness involved. So here the next date state is depends with respect to the current state action. So based on the current move, the next move will be decided by the opponent. So example is chess, tic-tac-toe problem and all. Then non-deterministic game. So here, based on the luck. So if we play with respect to the dice or cards, we can't able to say the next state or next move. So here it's purely based on the luck. So here there is no deterministic. So we can say non-deterministic games. The last one is the zero sum games. So if one player is gain, so another player will get lose. Say example in series of games, say example in chess or otherwise in cricket. So in cricket and all, the net run rate will be given. So if we add the net run rate of both two teams, it will be gets zero. That is called zero sum games. The total payoff. So in chess also, if one player is winning, so they will earn some positive points. The other player opponent may have the negative points. So if we add both the points, we will get zero. That's why we can say this kind of environments or scenarios are called as zero sum game scenarios. Then how we are representing the game environment in an artificial intelligence is, so game environment may be represented with respect to the following components. That is nothing but first initial state where the game is starting. What is the root node? Or otherwise where is starting, where is the initial node, right? That is the initial state, how, where, or otherwise where the game is starting. Next is players, how many players we have, which player has the move in the respective state. Then next is actions, so it may returns with respect to the legal moves, only legal moves are available. Next is the result, so that is nothing but new states after doing the action in the current state. Then terminal state, so in every state, it may check with respect to the final state or goal state, whether the game is over or not. That is called as terminal state. Then utility is nothing but final reward to the game game player. So if the player is winning, they will get the reward points as in positive. If the player is losing the game, so the loser may get the reward in the negative points. So this is a structured representation, allows us to treat games as a search problem in an artificial intelligence environment. So now let's move to the most important part in the adversarial searches, the min-max algorithm. The min-max algorithm is a regressive decision-making algorithm used in two-player games. So it assumes both players are playing optimally. So here there are two players are involved. So first player is Max. So Max is always tries to maximize the score. The next player Min. So Min always tries to minimize the score, right? According to the Max player point of view. So each board state is assigned with the numerical value. So the positive value will give the favor to the max. So negative value will give the favor to the min. So min-max explores the entire game tree to determine the best possible or otherwise best optimal move. So let us see the working of min-max algorithm. So the min-max algorithm works by using the depth first search, right? So may using the depth first search technique. So here what are the steps means, first it may generate the complete game tree from the what is that leaf node or otherwise up to the terminal states. Then it will assign utility values for each and every terminal nodes. So here we are applying backtracking. So we are backtracking the tree from the leaf node to the topmost node or otherwise to the root node or initial node. So here the max node chooses the maximum value. The min nodes chooses the minimum value. That is nothing but the max player always tries to maximize the value. The min player always tries to minimize the value. So it will continue until reaching the root node or initial node. So the final value at the root determines the optimal move or otherwise optimal path can be selected with respect to the root node to the leaf node in optimal way. So let us see the example so that you can able to understand. This is a uh, example game tree we have taken. See here, this square is representing the max player, the round is representing min player, right? So here we have the value only in the leaf nodes. So this is a leaf node, this is a root node, this is a leaf node. So here we have three levels: level 0, level 1, level 2, and level 3. So if it's winning, so that is nothing but plus 1. The value for the winning is plus 1 according to the max player. Then draw means 0. Lose means that is nothing but minus 1. So see here what I'm going to do here, I'm going to backtrack from leaf node to root node. How I'm going to backtrack with respect to the max as well as minimum level. So max level or otherwise max player always tries to maximize the value. Min player always tries to minimize the value. See here, first is maximum, then second is minimum, then again third is maximum, fourth is a leaf node. The values are given already. So we know the results in the leaf node. So now what is the level is this? This is the max level. So here we need to take only the maximum value. So here according to this node we have two childrens. So that is nothing but W as well as D, that is nothing but winning as well as draw. So here the value for numerical value for winning is plus 1, a numerical value for draw is 0. So we need to take the maximum. The maximum is W. We need to take maximum only. So this is W. So what is maximum from this L and D? So the maximum is D because L is minus 1, D is 0. So we will get D. So here the maximum is W. According to this node, D draw is maximum. According here, W win is maximum. So again here draw is maximum. This is maximum layer. Yes, we have filled the maximum layer by seeing the children nodes. Now this is the minimum layer. Next next level is the minimum level. So in this we need to check the children nodes of this. So win and draw. So which is minimum? Draw is minimum. So I need to take draw. So here again draw. So here I can take draw. So here also I can take draw. So in all these three cases, I have draw, right? So because here we are selecting minimum, then what is the first root node or first zeroth level? That is nothing but max. In max, I need to take maximum value from this. That is nothing but maximum is nothing but draw. So from this, we can able to conclude in this game tree, only possibility is to get draw, right? To get draw or otherwise to lose. That is the optimal. So either through this way, this is optimal, or otherwise this is also optimal, or otherwise this is also optimal, right? So this is how we can able to find the optimal path. Say if suppose if if this is given us, right? So if this is given us w, then we are getting w here. So obviously the w will say, instead of draw, if we have the winning condition here, so this will be becomes winning. So here winning, so this is also be winning. So here what it will get, we will get win. Okay, so here in the first level, so according to the maximum max player, so first level is max, second level is min, third level is max, and then fourth level again min. But here fourth level is the, or otherwise level 3 is the terminal nodes, or otherwise we can say the leaf nodes. This is how the min max algorithm can choose the optimal path to get win. So here what kind of principle is used means, so here the backtracking, right? So here what kind of search strategy we are using, that is backtracking search strategy. Okay, thank you all.